Oh, it was off.
Was
Sorry.
off, right. A little introduction. I'll tell you about photochemical mechanisms and then some of the photosensitizers that we've used to do this kind of peculiar kind of antimicrobial photoinactivation. So you've all seen a Jablonski diagram up here showing that you get both singlet oxygen and type 1 reactive oxygen species, and we think that the other big killer in addition to singlet oxygen is hydroxyl radicals. So these are the two killer ROSs, and because they're highly reactive, they can damage almost anything that lives, and for antimicrobial, all the different pathogens are susceptible to being photooxidized. So in the antimicrobial business, you kind of have to take some cognition of the different kind of cell walls that these bugs have. So it's kind of known that gram-positive bacteria have very permeable cell walls, and any photosensitizer can get through this kind of non-existent permeability barrier. So cationic, anionic, neutral, almost anything will kill gram-positives. But the gram-negatives are different. They have a very strong permeability barrier. They have a double plasma membrane with lipopolysaccharide and peptidoglycan. So it's a big struggle to get anything through those. And fungi have something that's intermediate. They have, a reasonably porous but not very porous layer of beta-glucan and chitin. So but there are photosensitizers that will efficiently kill all of these. So in principle, you can kill many logs of all of these. So getting into photochemical mechanisms, everybody knows about energy transfer from the triplet state to ground state oxygen, which happens to be a triplet. So the selection rules say this is a spin-allowed transition, and it can give you singlet photosensitizer and reactive singlet oxygen. Type 1 is a little less clear. Everybody knows it involves electron transfer. Where do the electrons come from? Do you get a radical cation, a radical anion? Do you get transfer to oxygen to give you superoxide? Do you need a source of electrons, a reducing agent such as NADH to supply the electrons? Superoxide is definitely formed, that's clear, but hydroxyl radicals is what does the killing. Where do the hydroxyl radicals come from? A lot of people talk about Fenton chemistry. Fenton chemistry needs free ferrous iron to react with hydrogen peroxide. But if you look at this is a simple one electron transfer from the radical anion to hydrogen peroxide to give you hydroxyl radicals. And if you look at the redox potentials, this is very low. So this is a dead easy electron transfer reaction. How do you distinguish type 1 from type 2? Well, everybody knows that deuterium oxide increases the singlet oxygen lifetime, potentiates type 2. Azide is a well-known physical quencher of singlet oxygen. You can get quenchers of hydroxyl radicals, more or less specific. People kind of say, well, they're going to quench anything. They're antioxidants. So a lot of people criticize these. Singlet oxygen sensor green, you've heard quite a bit about that. It's relatively specific. It's not 100% specific at all. But, it's dead easy to use. So a lot of people like using singlet oxygen sensor green. And 4-hydroxyphenylfluorescein, pretty specific for hydroxyl radicals, actually. I'm quite pleased with how HPF performs. So, if you've got a fluorescent probe for singlet oxygen, a fluorescent probe for hydroxyl radicals, you should be able to figure out what's going on. There are unambiguous detection methods. You can use 1270 nanometer luminescence for singlet oxygen, and you can trap hydroxyl radicals with specific spin trapping probes that allow you to do electron paramagnetic resonance. There are authentic sources of type 1 and type 2, so the Fenton reaction is a really good source of hydroxyl radicals. It's dead easy to do. And then there's another reaction between hydrogen peroxide and hypochlorite that produces singlet oxygen. We called it the Aguinaldo reaction because he was the first one to tell us about it. Again, this is probably not 100% specific. There's probably some hydroxyl radicals produced here. We started off kind of getting into this by accident. We had a couple of photosensitizers, methylene blue and a polylysine chlorinese 6, and we were trying to figure out how to get how much type 1 and how much type 2 was going on. So we did by trying to quench the singlet oxygen with sodium azide. And we thought, okay, right, fine, you know, the polylysine chlorinese 6 conjugate is more type 2, so it should be quenched more by azide. Methylene blue is more type 1, so it should be quenched less. But we did not expect potentiation, I have to say. That was a bit of a surprise. So here is gram-positive Staph aureus with addition of azide. You get about 2 logs more killing. And here is gram-negative E. coli, about 1.5 logs more killing when you add azide. And remember, we expected to see quenching. That's what everybody assumed we would see. If you look at the polylysine chlorinese 6 conjugates, as you might expect, you get quenching of killing. Here's 3 logs of quenching. Not so much here, but no, sorry, there's total quenching here. So quenching of type 2, but potentiation of type 1. So what on earth is going on here? If you take Fenton reaction, you get about 3 or 4 logs of potentiation. It's quite dramatic. From here to here is about 3 logs, about 4 logs. So with something that produces hydroxyl radicals, you get a lot more killing when you add azide. And you use the Aguinaldo reaction, the singlet oxygen chemical generator. As you might expect, you get inhibition of quenching, about 3 or 4 logs of quenching because it's singlet oxygen. So this was our initial hypothesis, that we were producing hydroxyl radicals, and the hydroxyl radicals were going to react with azide to produce azide radicals, which is, if you look at the redox potentials, clearly this is going to go very easily. And then we had this idea that although azide radicals are less reactive than hydroxyl radicals, they may survive longer to penetrate deeper into the microbial cell. So this was our idea that weak means strong. You know, it's less reactive, but it can penetrate more, so you get more killing. We collaborated with Tad Sarna in Poland, who actually does spin trapping in ESR. We don't have that facility. And he actually found evidence of azide radical. This spin splitting pattern is diagnostic of azide radical. There's the simulation. So we're definitely forming azide radicals here. You got the same spin splitting from Fenton reaction, which is an authentic source of hydroxyl radicals. So this was kind of backing up our idea that you got the hydroxyl radicals and then they gave you the azide radicals. However, this put the spanner in the works. You got the same spin splitting in the absence of oxygen. In the absence of oxygen, you cannot get hydroxyl radicals, right? So something else going on. Okay. There's actually still some killing of bacteria with azide in the absence of oxygen. So this is in the presence of oxygen, and in the absence of oxygen, there's no killing at all without azide, as you'd expect. There's no PDT in the absence of oxygen. But in the presence of azide, there is still some killing in the absence of oxygen. Not quite as much, but still some. So this is what we're thinking of calling type 3 photochemical mechanism, which is oxygen independent. We still need to do a lot more work on oxygen independent photokilling. You can't call it photodynamic because that implies you have oxygen. I've been firmly told that. So we call it oxygen independent photoinactivation. But it's quite interesting. So now we have a new hypothesis that we're getting direct electron transfer from methylene blue, from azide to methylene blue, forming the radical and the radical anion. And this can happen, of course, in the absence of oxygen. So they said, okay, this is wonderful with methylene blue. What about some other phenothiazinium dyes? You know, because there's a whole palette of phenothiazinium dyes. So we took a whole bunch of them, three azures, azure ABC, methylene blue, toluidine blue, new methylene blue, and dimethyl methylene blue. And we said, well, wonder if azide can potentiate killing with all of these. We managed to do illumination with a single light source. You know, it's not perfect overlap, but it's red light, and these are the absorption spectra of all these dyes, so it's not too bad. Turns out that with probes, with the singlet oxygen sensor green, there was inhibition in all cases, as you might expect. It's detecting singlet oxygen. It's well known that azide quenches singlet oxygen. So as you'd expect with the singlet oxygen sensor green, in every case there was quenching. With HPF, there was potentiation in most cases. Not all. There were some where you got quenching of HPF by adding azide, but in most cases there was potentiation. It's actually quite interesting to think how azide can potentiate hydroxyl radicals. We haven't quite figured that out yet. If you look at the effect of 10 millimolar azide on bacterial killing, the results are mixed. I'm not going to ask you to look at these graphs because I've got a summary coming up, but basically in some cases of these phenothiazinium dyes, it potentiated killing, and in other cases it inhibited killing. So it was kind of a mixed bag, and we also had different bacteria, and then we had wash and no wash. So it was a little complicated system. But what I've got here is I've plotted logs of inhibition or logs of potentiation for these 6 phenothiazinium dyes. The reason we don't have Azure C on here is that the reviewers pointed out that Azure C was sold at only 40% purity, so we couldn't really include this in the study, but never mind. What you see, if you look at these hashed columns for E. coli with a wash, in every case, there is potentiation. If you look at Staph aureus with no wash, it's mostly inhibition, and the other two are kind of in between. So it does seem to depend on whether you have a gram-positive or gram-negative bacteria, and whether you have or have not washed away the dye. And if you think about it, E. coli bacteria with a wash, the dye is the most firmly bound, right? Because E. coli are more negatively charged than Staph aureus. And if you wash the dye away, the remaining dye has to be firmly bound to the bacteria. So it appears that when the dye is firmly bound to its target, it's more likely to do type 1 photochemistry and to be potentiated by azide. So then, okay, we thought at that time, we were talking about pseudohalides, right? Azide is a pseudohalide. It's a triatomic sort of anion that behaves as if it's a halide. And there are others, and one of the ones that we thought was interesting was thiocyanate, SCN-. So you have thiocyanate in your body, you have it in your saliva, you have it in your lungs, in the secretions in your lungs. And why is thiocyanate present? It's to kill bugs, believe it or not. So you've got peroxidase enzymes in your neutrophils and various, even in your saliva, and these peroxidase enzymes react with thiocyanate to produce reactive killing species that kill the bugs. So it's clinically relevant, actually. Azide is not clinically relevant. I completely agree. Azide is poisonous. There is no way you can use azide clinically. But now we're going to get into some more clinically relevant salts. So again, you know, thiocyanate does potentiate killing by methylene blue, PDT. Here you see you add more thiocyanate, there's a lot more killing. The Staph aureus, probably 2 logs. E. coli, maybe 3 logs. So it kind of works the same as azide. Tadsana did this looking at the effect of how much oxygen you're consuming, you know, because we wondered if we're doing oxygen-independent stuff again like with azide. But amazingly enough, when you add thiocyanate, it gobbles up the oxygen. It really does. And even more telling, if you do this in D2O, it gobbles up even more oxygen. So this is completely different from azide, something completely odd's going on here. he found that thiocyanate quenches the phosphorescence from singlet oxygen. So, you know, the gobbling of oxygen is potentiated with D2O. It quenches singlet oxygen phosphorescence. Clearly, thiocyanate is reacting with singlet oxygen. It's no two ways about it. And here the potentiation is strongly oxygen dependent. So if you remove the oxygen, you don't get any killing. So again, this is different from azide. When he did spin trapping, again, another surprise, the spin trapping signature he got was of sulfur trioxide radical anion. And God, we did not expect that. You know, it took us a while to figure out what's going on there. But there's the simulation of it. You can produce sulfur trioxide radical anion by photolysis of sodium sulfite. And these two spin trap splitting patterns are completely superimposable. So there's no question that we had sulfur trioxide radical anion. So how on earth can you get that? So here's the mechanism. Here is thiocyanate reacting with singlet oxygen, kicks out cyanide, and gives you, this is sulfurous acid, actually. And then you can get the sulfur trioxide radical anion. So if this is true, you should be able to demonstrate the production of cyanide and sulfite. And you can do a Prussian blue assay for cyanide, light-dependent production of cyanide. You can measure sulfite by malachite green bleaching and a light-dependent production of sulfite. Can sulfite potentiate bacterial killing? The answer is it actually can if you do it at a very low dose. Sulfite is a reducing agent, so if you put it in at a high dose, it just quenches the ROS and it's gone. But if you put it in a low dose, it actually does potentiate killing. And if you put cyanide in at a relatively low dose, 1 millimolar, that actually potentiates killing. And if you mix the cyanide and the sulfide and put them in, again, it potentiates killing. So it appears that this sulfur trioxide radical anion may just be indicating of the mechanism. We're not claiming that that is a reactive radical, but there is something reactive being formed. As I say, the sulfite effect is biphasic, because if you have it at a high concentration, it quenches killing. So we've got azide, which is not clinically relevant, thiocyanate, which may be, and now we've got iodide. So potassium iodide is, you know, non-toxic. Everybody's going to take a potassium iodide pill if there was ever a nuclear attack to prevent against thyroid cancer. And again, initially we had the same idea. We're going to produce the hydroxyl radicals, which was going to produce iodide radicals. Good potentiation of methylene blue PDT by adding potassium iodide. Several logs of potentiation in both a methylene blue and a light-dependent manner. And even you can look at potassium iodide concentration. With gram-positives, it works at relatively lower, but for gram-negatives, you need the 10 millimolar. Potassium iodide quenches activation of HPF, which was telling us that maybe it is reacting with the hydroxyl radicals. You can see production of iodine. If you produce iodine radicals, you will always produce iodine, because two iodine radicals will just come together to give you molecular iodine. So that is being produced. If you put potassium iodide into Fenton reagent, you get a huge potentiation, 6 logs more killing if you put iodide in. It's a huge effect. If you put potassium iodide into horseradish peroxidase and hydrogen peroxide, again, huge effect. At least 6 logs more killing just by putting 10 millimolar potassium iodide in. There was some suggestion that the iodine that we were producing might have been responsible for killing the bugs. That's probably not the case, because it's not quite this graph, but We did some studies by shining the light on the mixture of potassium iodide and methylene blue and then putting the bacteria in afterwards. And that didn't really kill. Does it work in vivo? So this is a bioluminescent study using MRSA, a bioluminescent gram-positive bacteria in burns. And because you can do the bioluminescence imaging, you can follow this thing. So these are the controls: light alone control, dark control, burn alone control. This is PDT with methylene blue. You know, by the time you delivered a lot of light, you've eliminated the bioluminescence. But when you put potassium iodide in, with about a third of the light, you've eliminated the bioluminescence. So it does potentiate the loss of bioluminescence, again, by about a log. And so fullerenes, we've done some studies with fullerenes. We collaborate with Long Chang. These are also things that do type 1 photochemical mechanisms. Long Chang has made a lot of amazing buckyballs. He puts these polycationic chains onto the buckyballs, which make them good antimicrobial photosensitizers. There's some more of them. Absorption spectrum, as you might imagine. You can use visible light with buckyballs. You know, you can also use UVA. So we use UVA and white light. As you might expect, you need to use more white light because the absorption to some degree is biased in the UV region. So this is LC16. It has a chain, 10 cationic charges and 10 tertiary amines to enable these buckyballs to bind to the bacteria and produce ROS in the right place. We added iodide. This is Acinetobacter baumannii. It's another gram-negative. Make a change from E. coli. Again, we get a couple of logs of potentiation by adding potassium iodide. And again, this works in vivo. This is an abrasion infected with Acinetobacter baumannii. And again, you know, without the iodide, you need these 20 joules. With the iodide, it's gone maybe after about 5. So it really helps the in vivo inactivation of bacteria. White light, a little bit less effective, but similar sort of thing. Quantify these loss of bioluminescence, so you see about a log better effect when you add the iodide. So the last one I want to tell you about is titania. Titania photocatalysis is actually quite interesting. It's been done for a long time, and you know, it's used industrially. Right? If you want self-sterilizing surfaces, right, you put titanium dioxide in, and whenever a bacteria lands on titania and there's light around, it gets killed. It gets killed by ROS, as you might expect. But titania is slightly different from regular photosensitizers. So you get this electron transfer here. Basically, the light shifts electrons from the valence band to the conductance band. So you get electrons coming out here, producing superoxide. But here you get holes. These H+ is actually a hole, which means the absence of an electron, right? And these holes can react with water to give you hydroxyl radicals. So as opposed to traditional electron transfer, you're getting 1 ROS per electron transfer. Here you're getting 2, and this one is actually direct hydroxyl radicals. You don't need to make these from hydrogen peroxide and all this stuff. So titania is kind of interesting. And we actually found that potassium bromide potentiates titania. So we tried bromide with methylene blue. We tried it with buckyballs. There was absolutely no potentiating effect at all. But with titania, there was. And not only that, you know, this is big. This is 5 logs of potentiation by adding iodide. There's no potassium bromide here. Right? No killing, virtually. Put bromide in, you get 5 logs of killing. Same with E. coli. So it's bromide, huge effect by adding bromide. Much bigger than we ever saw with methylene blue or with buckyballs. Works with Candida. We thought, well, can we do it with Candida? Yes, we can. About 5 or 6 logs potentiation of killing of Candida. So we also, titania works well with iodide and even with nitrite. Nitrite is an interesting one. We've just started to use nitrite. Again, nitrite is a clinically relevant compound. It's used in food preservation. It's part of the pharmacopoeia. You can actually administer people nitrite. You know, it's an NO donor. It's quite interesting. Iodide and nitrite work with methylene blue and with buckyballs. Bromide only works with titania. So we actually think the mechanism of photoactivation of titania is slightly different. We believe it is much more similar to hydrogen peroxide and a peroxidase, which I showed you a few slides back, and that the titania is probably producing these long-lived reactive intermediates. So when I get back, one of the folks in the lab will have shone light on titania and bromide or iodide and then put the bacteria in afterwards. And I'm expecting to see that a somewhat long-lived reactive intermediate is formed from titania, which is not the case for methylene blue or for buckyballs. Okay, so the conclusions are that photochemical potentiation involves adding a relatively simple chemical compound, a non-toxic inorganic salt, but it has complex mechanisms. It's not obviously clear what's going on a lot of the time, and you keep scratching your head and revising your hypotheses. Clearly, electron transfer mechanisms from phenothiazinium dyes appears to be important. It's known that fullerenes can produce both singlet oxygen and hydroxyl radical. They're sort of similar to phenothiaziniums to some degree, although there are differences. Titania is the only photosensitizer that's potentiated by bromide. I say iodide and nitrite are clinically relevant, they're already approved, and it is possible in some of these circumstances that we can do oxygen-independent photoinactivation. So these are some of the folks that do. Tad Sana, we've collaborated with Tad. He's did all the ESR stuff. These are some of the folks in the lab who've done the studies and the funding agencies. And thank you all for listening.
Okay, so any questions? Comments? Comment or question? Okay.
What is your interest as far as titania regarding photoinactivation?
I think I got into titania more because of the interest in the photochemical mechanism. We really wanted to see what is going on. Now, I've reviewed a few papers when they've been proposing to do PDT with nanoparticles loaded with titanium dioxide, right? So people are starting to propose that. You know, the folks that are big into nanoparticles can deliver these titania things to various places. So it is possible to do PDT with them. And, you know, if you understand the photochemical mechanism and you understand whether you can potentiate it with salts, you could improve these titania nanoparticles.
So you mentioned this compound works for antibacterial, antifungal. How about cancer? Would they work?
Well, with the salts, it's kind of difficult to get them into the cancer cells, you know. So you can use methylene blue, you can use fullerenes, you can even use titanium nanoparticles to kill cancer cells. Could we potentiate it by salts? You know, I think we might try, because if you produced like a nanocapsule that had a photosensitizer inside and also potassium iodide or potassium nitrite, you could load these into a nanocarrier, and you could deliver the whole thing into a cell, and maybe you could see the potentiation.
To follow up on that, how about organic biocyanide? Would that work, or it has to be inorganic?
Organic?
Those organic salts, so the biocyanide.
Thiocyanate? Yeah, the thiocyanate works.
For example, phenol biocyanate.
Oh, that's not really a salt. Phenyl thiocyanate is more like an organic compound. We never tried it. I have no idea what would happen. I think we'd really just have to try it and see.
Maybe I can comment on that question. So Doug Meckers, many years ago, played with rose bengal, and he tried to do it with salt, most of them. And they worked beautifully. I mean, he could really generate a very logical curve with that in vitro, absolutely spectacularly. But as soon as you put it in vivo, everything was lost, yeah. So you never saw that kind of a thing. So if you could keep them together, maybe, but then if it's not exposed, it doesn't have the advantage of having the salt. So, yeah.
Yeah, you need millimolar concentrations. We've seen it with 100 micromolar, but 10 millimolar works best, yeah.
So, probably it's a bit naive questions, particularly concerning the type 1 interactions. It looks like you have this type 1, which is mainly production of hydrogen oxide. Is that the main oxygen-dependent killing mechanism?
You need hydrogen peroxide. So I think the titania is an exception, but for methylene blue and fullerenes, you need hydrogen peroxide in the path to making the hydroxyl radicals.
Yeah, that is the main mechanism for killing.
The hydroxyl radical is the mechanism for killing.
And is there some kind of method to basically identify the hydrogen mechanism and hydroxide, that you can, I mean, I know there's an absence of single oxygen, but is there some...
So the methods for identifying hydroxyl radicals are the HbF activation and the spin trapping, and we've done both of them. And it's clearly you generate a lot of hydroxyl radicals. There's no question about that.
And then you have this type 3, which is probably will happen related to type 1, that's oxygen independent. And how do you differentiate that?
We define type 3 as oxygen independent, right?
Right.
So if you can see microbial killing in the absence of oxygen, the radical cannot have oxygen in it. So, this is going to be an inorganic radical, an iodide radical, or an azide radical.
Is that possible to do that in vivo?
I have no idea. It's sort of difficult getting an anaerobic infection. There are animal models, but they're kind of deep inside because there's no oxygen there.
So how would you, for type 3, the hydroxyl radical doesn't come from oxygen?
There's no hydroxyl radicals in type 3. These are inorganic radicals.
No, but you just said that the type 3 would have to be without oxygen. So right. Where would the hydroxyl radicals be?
The hydroxyl radicals are type 1. In type 3, it's an inorganic radical. It's iodide radical.
Oh, inorganic is different. Yeah. Okay, fine.
Of course, maybe everybody is thinking, how comes that normally the type 3 doesn't happen together with oxygen as well? Because you may have both together.
You may have. Yeah, absolutely. And we have evidence that the azide radicals are doing some killing.
Okay. So, since we don't have any more questions, let's thank again Professor Hamblin for the nice talk.